We go over nucleophilic substitution reactions, also known as SN reactions. So we have got the word nucleophilic that we have to understand in this kind of reactions that we're talking about. So a nucleophile itself is a substance that loves a nucleus, and in this case it is a chemical substance because this has to do with reactions. And so mostly we are going to represent a nucleophile with N and a U. We'll put lone pair of electrons like that. We are going to have another compound. Now because this we are going to concentrate on it on alkyl halides, then we are going to represent an alkyl halide. Now alkyl halide is simply an alkane where you've removed one hydrogen and substituted it with an halogen. For example, methane is supposed to have 4 hydrogens. We remove one hydrogen, we substitute, let's say, with a chlorine, fluorine, bromine, and such. And so this one is an alkyl halide. Now an alkyl group, we mostly represent it with R, and an halogen we're going to represent it with X. So this is going to be the symbol that we are going to be using for an alkyl halide. And so I'm going to put an alkyl halide here. So the kind of reaction that happens here is that this nucleophile, a nucleophile is rich in electrons. In other words, it has got electrons which are not bonded. So this this one lone pair of electron, which is 2, a lone pair is supposed to have 2 electrons, is going to attack the alkyl halide like that. And so when this happens, so specifically what is getting to attack is the alkyl group. And this bond between the alkyl group and also the halogen is going to be broken. The halogen is going to take those 2 electrons. And so what we are going to see at the end is that the nucleophile is going to form a bond with the alkyl group, and the halogen is going to be alone with a lone pair of electrons, and so it's going to carry negative charge because it has got more than the electrons that it is supposed to have. So this is the kind of reaction that gets to happen. This is called a nucleophilic substitution. So we have substituted a nucleophile for a halogen. So an example that I can talk about is, let's say we have got this compound. So from what you're able to see, we have got the aldehyde functional group here, which is attached to a phenyl group or a benzene. Let's say this one gets to react with this compound here. So what kind of reaction is going to happen? Well, what we are going to see is that we first need to identify which one is going to be the nucleophile. So the nucleophile is the one which has got lone pairs of electrons that are supposed to attack the electrophile. So in this kind of reactions, we have got the nucleophile and the electrophile. The electrophile is that substance or that compound which loves electrons. Electro is the one which is meaning electrons, and the phile is meaning loving. So the electrophile loves electrons. This is the nucleophile. It loves the nucleus, and so it loves the nucleus of another compound. So specifically this part, which is negatively charged, which has got lone pairs, is the one which is going to attack, and is going to attack the carbon which is here. So when that gets to happen, because we have got a carbon here and it has got already 1, 2, 3, 4 bonds. Carbon can't exceed 4 bonds. So because of that, one bond here is going to be broken, and those 2 electrons are going to go there. And so what we are going to have as a product, still going to have this ring. Now instead of having 2 bonds, we are going to only have 1 bond like that. Then we are going to have an hydrogen here. So this carbon has come and it is going to attach here, right? So I'm going to show that there is a carbon here, and then I'm going to show the triple bond with a nitrogen there. So we have got a carbon here, which is this one, and then there's also a carbon here at the center, which is the carbon here. Or if I want, I could have shown the carbon which is here, which is coming from this compound. So this is a nucleophilic substitution reaction. Now in this kind of reaction, what we're able to notice is that we have got this compound which we are calling as the nucleophile, which gets to donate protons. When we say protons, we simply mean, so in this case, let me not even say protons because we don't have hydrogen. So this one is going to donate electrons. So if we are saying protons, we are meaning hydrogens. So this one is going to donate electrons to the other one. The other compound is receiving those electrons. So the nucleophile is also called an electron pair donor. So an electron pair donor is referred to as a Lewis base, and an electron pair acceptor is referred to as a Lewis acid. So because most of the times nucleophilic substitution reactions involve acids and bases, we are supposed also to understand acids and bases, their strength, and also the kind of reactions that they are going to undergo. Now, if we get to look on the periodic table, we have got groups and also periods. So we also need to understand the strength of acids going in the groups and also in the periods on the periodic table. So if I start just writing a simple one, let's say we have got nitrogen in group 5, we have got oxygen, and then we have got fluorine. So this one is in group 5, this one is in group 6. Supposed to have before fluorine, supposed to have something in group 7 there. Let me just get to check that out on the periodic table. So we have nitrogen, fluorine. Yeah, fluorine is supposed to be here, and then we have got the group 7, the group 8 elements like the neon, the argon, like that. But most of the times these group 8 elements are not involved in reaction, so I'm going to remove them. So I'm just going to end on the fluorine. And then going down, we have got chlorine, we have got bromine, we have got iodine, we have got argon. Sorry, not argon, but astatine. So when we get to look at these elements which we have like this, when we are going in this direction on the periodic table, what we are doing is we are increasing electronegativity. So the most electronegative atom on the periodic table is fluorine. When you talk about electronegativity, this one, whenever it is competing with some other element to see which one is going to pull electrons in a bond, fluorine always wins. For example, when we are having a bond between fluorine and hydrogen, this of course is a covalent bond. Now because fluorine is more electronegative, even if these two electrons in this bond are being shared, fluorine is going to pull those two electrons more towards itself because it has got a stronger pull of electrons. So in as much as this is sharing of electrons, this one is going to have electrons more closer to it even if they are shared, and so it gains a partial negative charge, and the hydrogen is going to gain a partial positive charge. The reason as to why this one even gets to gain a partial negative charge is that it has got electrons closer to it, and we know that electrons are negatively charged. And because the negative portion has gone away from the hydrogen, is going to remain more positive. So when these elements are forming acids, of course when we have got these elements getting to react with an hydrogen which we refer to as a proton, is a characteristic of an acid. And so we are going to have these acids like hydrogen fluoride, hydrochloric acid, hydrogen bromide, hydrogen iodide, these. So we need to know the trend, which one is going to be the strongest acid. So in this kind of reaction, the strongest acid is going to be this one here. The weakest acid is going to be hydrogen fluoride. So therefore, the strength of acid increases as you go down the group. Now, why is it like that? We know that hydrogen fluoride, of course, just fluorine itself is the most electronegative atom on the periodic table. So because of that, it means that it is strongly held to this hydrogen. The bond between hydrogen and fluorine is such strong that it is not easy to break. So the strength of an acid is proportional to how easy it is for that hydrogen to be lost. So because it is not easy to lose this hydrogen, because the bond is so strong, then this is going to be a weaker acid. Now because iodine is more less electronegative, meaning that the bond between iodine and hydrogen is weak, meaning that hydrogen can be easily lost in this bond. Because it can easily be lost, this makes this acid to be a much stronger acid. So even when we are talking about these nucleophilic substitution reactions, it means that this kind of reaction is going to be faster. The reaction involving hydrogen iodide is going to be much faster than the reaction involving hydrogen fluoride. The reason for that is this bond can easily be broken as compared to this bond which is in hydrogen fluoride. So that is when we are talking about going down the group. Now, when these acids get to lose the proton, they are going to form conjugate bases. And so when this proton is lost, we are going to have the conjugate base, which is the fluorine ion. Even here, we're going to have the chlorine ion, which is the conjugate base, bromine ion, iodide ion. So the proportionality of acids and bases is inverse. So if this is a very weak acid, it means that the conjugate base is going to be a very strong base. So the strength of bases is going to be opposite. So the strongest base, what forms the strongest base is fluorine, followed by chlorine, bromine, and then iodine, going down the periodic table like that. So that is the strength of conjugate acids and conjugate bases. Now another thing that you need to take note of is that acidity increases from left to right of the periodic table. The elements that we saw, of course, we have got a carbon, we have got a nitrogen, we have got oxygen, and then we have got fluorine. So acidity is going to increase as we go in this direction on the periodic table, and also acidity increases as we go down, as we already saw. So we can also make some comparisons here. So let's say we have got a methane, so that is we have got CH4. Now instead of me writing it like this, what I'm going to do is I'm going to write a carbon with 3 hydrogens. The fourth hydrogen, I'm going to put a bond like that. And then again, I'm going to have H2. Now instead of me using this nitrogen, of course this I'm supposed to write ammonia NH3, but I'm going to write it like this. Then I'm going to put hydrogen like that. And then I'm also going to write a water molecule. Now instead of me writing H2O, I'm going to write HO and then hydrogen bonded like that. So my interest is with this hydrogen which is bonded because it is the characteristic of an acid. And then let's also have fluorine bonded to this hydrogen. So we are seeing acidity increases as we go in this direction. So we have got a carbon, we have got a nitrogen, we have got an oxygen, and then a fluorine. So this tells us that the strongest acid here is going to be hydrogen fluoride, followed by water. Water is also an acid, followed by ammonia, and then we have got this compound here, which is methane. So when this hydrogen is lost, we are going to have conjugate bases. And we know that when we have got the weakest base here, the weakest acid is going to form the strongest base. So the conjugate bases, we are going to have CH3 with a minus. This is going to be the strongest. We are going to have NH2, which is going to follow, and then we are going to have hydroxide, and then we are going to have the fluorine ion. So meaning that the hydroxide, this base, is much weaker in comparison to the amine here. So that is also how we are able to talk about the strength of acid going on in the period, and also the strength of the base. So we also have hybridization. Hybridization also affects the strength of an acid. What is hybridization? Well, we know hybridization is simply the hybrid orbitals that compounds get to form as they get to react. So every time when carbon is reacting with four different things, it is supposed to form sp3 kind of hybridization. So if carbon is bonding with the three different things, it's supposed to form sp2 hybridization, and when it is only bonding to two different things, is going to form sp hybridization. So it is not only carbon, any element, as long as it gets to bond with four things, well, it is not always bonding. At times you can remove this bond and replace it with a lone pair of electrons. Still, the kind of hybridization is going to have is sp3, right? And the shape that this forms is tetrahedral. And the shape that this one forms when it undergoes sp2 hybridization is trigonoplanar. This one is a linear shape. So now what will be the effect of hybridization on the strength of the acid and bases? So when hybrid orbitals have more s characters, when you have got a lot of s characters, that means that the electrons of the anion, the negative ion that is going to be formed, will on average be lower than the energy of the anion. So basically what I'm saying is that when you have got more s characters, there is going to be lower energy, because when we have got s characters and then we have got p characters, we know that p orbitals have got higher energy than s orbitals. So when we have got a lot of s orbitals, it means we have got a lower energy. And when you have got lower energy, it means you are more stable. So meaning that the most s characters we have, the more stable this acid is going to be, and the stronger it is going to be. So we can get to compare different acids in regard to their hybridization. So we have got alkynes, we have got alkenes, and we have got alkanes. We know that alkynes have got a triple bond, like that, meaning that the kind of hybridization that is going to be is only sp. Alkenes have got a double bond somewhere. Let's say they are like that. So the kind of hybridization that we are going to see in this is sp2. Alkanes don't have any double bond, and so the hybridization that we see is sp3. So because we have got less in comparison to here, so if you want to calculate the percentage s characters in these compounds, what you do is that you only have two characters here, one s, one p, meaning that the s characters here is 50%. And then if we go in this one, we want to calculate the percentage of s characters. What are we going to do? Well, we have got the three characters. Two of them are p's and then one s. So to calculate the percentage of s character, it is 1 out of 3, and then multiply that by 100%. And then to calculate the percentage of s characters in this one, we have got 4 characters, but out of them we only have 1, which is s. So that will be 1 out of 4 times 100%. So 1 out of 3 times 100, that is basically 100 divided by 3. So we are seeing that that is going to give us 33.3% s characters. And then in the other 100 divided by 4, that is going to give us 25% S characters. So we are seeing that in alkenes we have got a higher percentage of S characters than in alkenes, and in alkenes more than in alkanes. So meaning that alkenes are going to form stronger acids in comparison to alkenes and alkanes. So we can get to compare some examples. So when we have got this compound HC triple bonded like that, so what will be the name? We have got two carbons and we have got a triple bond, so this is going to be ethene. We can compare it with H2C where there is a double bond. This has also two carbons but it has a double bond, so this is ethene. And then we can compare with ethane, H3C, single bond H3, so this is ethane. So in here, the one we expect to be a much stronger acid is the first one, and then followed by the ethene and then the ethane. So if these are to form their conjugate bases, meaning that they lose one proton, so if the first one loses a proton, what we are going to have is HC triple bond, and then we are going to only have C with a minus charge. Then the second one we are going to have H2C double bond H2, just CH. We are going to lose one proton, so it's going to have a negative charge every time you have got less protons than what is expected. And then we have got H3C H2 like that. So in this case, the strength is going to, the strongest base is going to be the alkane, followed by the alkene and then the alkene, because we know that the weaker the acid, the stronger the conjugate base. So this is how acidity increases with respect to hybridization. So you look at how many S characters are present in those molecules. So let's also get to compare the strength of alcohols and carboxylic acids. So to get to compare this, I'm going to use an example. We are going to pick acetone and ethanol. So acetone, of course, we know that for an acid we're supposed to have this functional group, a carbon bonded to oxygen and then OH, which is this one we're able to see here. So this is acetone. And then let me also get to write this one. Right. So this is, we have got two carbons, 1, 2, this is ethanol. So I've got ethanol and acetone. Of course, this oxygen, you know that oxygen is supposed to have 8 electrons for it to be stable. So it's going to have 2 lone pairs. This one here is also going to have 2 lone pairs. This one here is also going to have 2 lone pairs. So let's say this one is getting to react, these two substances are getting to react with water. Water, of course, we know that it has got 2 lone pairs of electrons. I'm going to also write here. So water in this kind of reaction is going to act as a Lewis base or as a nucleophile, meaning that it loves the nucleus. So it's going to donate one of these 2 electrons. So what happens in this kind of reaction is that the water is going to attack this oxygen which is here. And when that happens, not actually the oxygen, but the water is going to attack this hydrogen. So when that happens, this bond is going to be broken. So this bond, the 2 electrons are going to be taken by this compound. Same here, what we are going to see is this is going to attack this hydrogen and the bond is going to be broken. The bond which is between the hydrogen and the oxygen, of course I've not shown it, is going to be broken and the 2 electrons are going to go there. So what we are going to see as a product, this oxygen is going to have more electrons, and so it's going to carry a negative charge because it has got more than enough electrons. And then this hydrogen is going to be taken by the water because it was attacked. So what we are going to have is water with 3 hydrogens, and so it carries a negative charge because it has got more than, so it's going to carry a positive charge every time a compound has got more than enough hydrogens. carries a positive charge. Same with this one down here, we are going to have it like that. So it's going to have also more than enough electrons carrying a negative charge, and then the water is also going to be charged like that. So in this kind of reaction, of course, we know that this is acetone. So the ion that is going to be formed is the acetate ion. This is ethanol. The ion that is going to be formed, we refer to it as the ethoxide ion, because there is an oxygen there. And then we have got two carbons which are bonded to hydrogen. So we call it the ethoxide ion. Right, so in this reaction, which one is going to be stronger than the other one? So carboxylic acids are weak acids mostly. So alcohols essentially do not give up a proton unless they're exposed to very strong bases. So this proton that you're able to see in alcohol is mostly it will not be given out. So because it is not mostly given out, what does that mean? It means that it is very difficult for us to form an ion from the alcohol. It is strongly held like that. And we know that this one, which is donating 2 electrons, is a Lewis base. This is a base, that is why it is forming a conjugate acid at the end. And this is a Lewis acid. Okay, it's an acid because it's receiving an electron pair. Now in this case, we will not refer to it as a Lewis acid because of the receiving of the electron pair. We'll just say it is an acid, of course, supposed to be a Bronsted Lowry acid. So because it is very difficult for it to lose this electron, this proton, what can we say? It is going to be much weaker, of course, we expect. So expect it to be a much weaker acid because it is very difficult for it to release its proton. Now, what is the reason for that? Why is it that it is difficult for it to lose that proton that it has? So that has to do with what we call the inductive effect. I'm going to show that again. We have got this as the acid, and then we have got the alcohol. Okay, like that. So there are two factors which are going to show us to why the acid is much stronger acid than the alcohol. So one thing is the effect of delocalization. So when we talk about delocalization, because in acids we have got a double bond, there is a resonance that gets to happen. So of course we know we have got two lone pairs of electrons here. So what happens is that this bond can be broken. The electrons are going to go there on the oxygen. And so when that happens, what we are going to form is something like this with a single bond. Then the oxygen is going to have more electrons like that with a negative charge. So because acids are able to form resonance structures, when you are able to draw more than one structure for the same compound, that is resonance. So that is delocalization. So because of that, because of delocalization as seen by resonance structures, any possible resonance structure that you are able to see, the ion, the negative charge, is going to be shared not only by one structure but by different structures because of resonance or delocalization. So because of that, the charge is going to be stabilized because it is not only on one compound. Because of that stabilization, anything that stabilizes charge makes the acid to be much stronger. So this makes the acids to be much stronger acids, or the carboxylic acids to be much stronger than alcohols. Apart from delocalizations, which we are seeing from the resonance structures, we also have the inductive effect. Now what do we mean by inductive effect? So inductive effect has to do with electronegativity. So in these compounds we have got oxygens which are more electronegative. So here we have got a carbon and then bonded to an oxygen. You know that oxygen is more electronegative. So the electronegative oxygen is going to further help to stabilize the charges that we are seeing on these atoms, right? We know that we are seeing negative charges in these atoms. So the electronegative atoms, which is the oxygen in this case, is going to help stabilize the negative charges. So because of that, the acids tend to be stronger acids. Now, why is it that they tend to be stronger acids? Because of the inductive effect. So by the inductive effect, what is going to happen is that this bond between the carbon and the oxygen is going to be pulling electrons towards itself like that. But you also have another oxygen here, meaning that also this side, the the oxygen is going to be more like be pulling the electron, right? So we have got this oxygen here which is more stronger, which is attracting more electrons because that's a lone pair of electrons like that. So we have also electrons, we can show the inductive effect like that. So in other words, there is a stability of the charge due to two oxygens which are stabilizing that charge. We don't only have one electron in this compound. I mean, we don't have only one oxygen which is stabilizing the charge. Now when we get to look at alcohols, we only have one oxygen which is going to be stabilizing the charge. So because of that, this compound is going to be much stronger acid than this one because of the inductive effect. The inductive effect just has to do with the stability or the stabilizing of the charges. So we can as well compare two acids to see which one is going to be a much stronger acid. Let me also say this is also an acid, but here let me put chlorine this side. Let's say we have got a chlorine there. So which one is going to be a much stronger acid in this case? Or to see which one is going to be a much stronger acid, we are going to look at the inductive effect. So in this one, we have got this oxygen of the functional group, which is more electronegative, and so the inductive effect, we are going to show arrows. So we are going to have an arrow going towards that oxygen. We also have another oxygen here, so the inductive effect will show arrows going towards that oxygen which is of the functional group like that. But in this compound, we are going to look again at those atoms which are more electronegative. So here we have got a carbon bonded to a chlorine, and we know that chlorine is a more electronegative than carbon. So we are going to have also an inductive effect like that. Even here we are going to have an inductive effect like that. Also still inductive effect going in that direction. So the inductive effect is also always going towards the more electronegative atoms. So because there is more inductive effect in this compound than in this one, you expect this compound to be a stronger acid than this one. So actually the pKa for this compound is 2.86. The pKa for this other one is about 4.75. The lower the pKa, the stronger the acid. So we are saying that the other one there is going to be a much stronger acid. So what are we saying? The greater acidity is attributed to the extra attracting inductive effect of the electronegative chlorine, which is here. So by adding the inductive effect of chlorine apart just from the inductive effect of the oxygens here, what is happening is that it makes the hydroxyl proton, so this proton here which is here, to be more positive. So the reason as to why we are even seeing, I'm showing the inductive effect going in this direction, is that we are talking about this proton which is supposed to be lost. So in other words, there is more inductive effect. This proton is more pulled in this direction. So if it is more pulled, in other words, we have more negative charge. So when we have got a more negative charge, it means this one is also going to be more positively charged. But because in this one there is even more negative charge because of the more increase in electronegativity, so we are going to increase a negative charge. So because of that, we are also going to increase the positive charge of this hydrogen. So when we increase the positive charge of this hydrogen, it means that it is more able to be pulled or attracted by other substances which are able to attract it. Because of that, that makes this compound to be a much more stronger acid. We can get look at these examples looking at what we've looked at. Which compound in the following pairs would be the most acidic? So we have got this one and this one. So if we see we have the same number of carbons, 1, 2, 3, 4, even here 1, 2, 3, 4, and they are all acids, but the only difference is that we have got a fluorine here, here we have got a bromine. So what would we say? Which one is going to be a much stronger acid? So we have got a bromine and they are all at the same position. Well, we are going to say this one is going to be a stronger acid. What is the reason? That is because fluorine is more electronegative, and so because it is more electronegative, the charge is going to be more dispersed. So because of the inductive effect, by the inductive effect there is dispersal of charge. So you are going to have the charge being dispersed when this compound forms an anion. So what happens is that when this hydrogen is lost, we are going to have this becoming oxygen with a negative charge. So this negative charge is more easily dispersed. So because of this compound, which is this fluorine, which is more electron negative, the negative which is going to be formed in the anion is going to be dispersed. In other words, it's going to be more like shared by the inductive effect. And so this one ends up being a stronger acid in comparison to this one. Let's consider this other one. Which one do we expect to be a much stronger acid? So also we have got the same number of carbon atoms, except fluorine here is attached at the second carbon, here it is attached at the third carbon. So which one do we expect to be a much stronger acid? So the answer still lies in the dispersion of the charge or the inductive effect. So the closer an atom or an halogen is to the functional group, the more it can disperse the charge. So you expect this one to be a much stronger acid. Why? Because the fluorine is much closer to the functional group. Because when you increase the distance, because the negative charge is going to be formed on this oxygen when this proton is lost. So by the inductive effect, when this negative charge has been formed on this compound, for it to be attracted, to be shared with this fluorine at this end, the distance is so high, so there's going to be a weak sharing of that charge. So when the charge is shared weakly, it means it's not going to be stabilized well. So it's going to be more stabilized in this compound than in this compound. So the second one is the charge is going to be easily dispersed in the anion that is going to be formed, because the fluorine is much closer to the functional group. Let's consider this one. Which one is going to be the much stronger acid in this pair? To determine that, we need to know the structures of these two compounds. So I've got a carbon that has got two hydrogens. So I'm going to show just line structures. So I've got how many carbons? 1, 2, 3. So we only have 3 carbons. So I'm going to write this 1, 2, 3. And then in this one, we have got a chlorine which is attached at carbon number 1. So I'm going to attach a chlorine here. And then we have got at carbon number 3, we have got this functional group. So we have got, sorry, that is at carbon number 3, we have got double bond with oxygen, and then we have got an OH. So this is the structure. And then we go in the other one, we still have 3 carbons, 1, 2, 3. And then we have got 2 chlorines on the first carbon. Okay, so we're going to have the first chlorine, then another chlorine. Of course, we have got an hydrogen that we can't see, and then we have got also this functional group of the acid. So that is what we have. This is the structure. Now, which one do we expect to be a much stronger acid in this? So when we look at this, they basically are the same, except that for this one we only have 1 chlorine here, but we have got 2 chlorines. So by the inductive effect, this one we expect it to be a much stronger acid. What is the reason? We have got 2 chlorines, and we know that chlorines are more electronegative. So B is going to be stronger due to 2 electron withdrawing in chlorines. So these 2 chlorines are going to be withdrawing electrons from the, if this hydrogen is lost, the anion that is going to be formed, that negative charge is going to be dispersed, or is going to be shared, because electrons are going to be more pulled even by these 2 chlorines. So they have more stronger pulling effect than only one. That is why we end up this one being also much stronger. Okay, so apart from that, we also have more effective stabilization of the ion due to the same inductive effect. Apart from the sharing of electrons by these 2 chlorines, the inductive effect is also going to be able to stabilize this compound more because of these 2 chlorines. Let's consider this one also, which one is going to be much stronger. So also we need to write the structure. We have got only 2 carbons, this one and this one. So we are going to have this and that. So that's a compound. But on the first carbon we have got 3 chlorines. And then we have got a double bond with oxygen, and then OH on the second carbon. Same going to the other one, you only have 2 carbons, but you only have 2 chlorines, and then we have got OH and O. So which one do we expect to be stronger? Well, we can basically see that this one is going to be much stronger because is going to have a much stronger pull of electrons because of the 3 chlorines. So the charge which is going to be formed here is going to be shared well, right? So that is why this compound is going to end up being a much stronger acid as compared to this one, because anything that stabilizes the charge, increases the strength of the acid. So we have got more chlorines which are able to stabilize the charge that is going to be formed when the hydrogen is lost. Let's also consider this one. So we still have only 2 carbons, so I'm going to show like that, but we have got a fluorine on the first carbon, and then we have got, this is an acid. For the second one also we have got only 2 carbons, but on the first one we have got bromine instead, and then we have got also the carboxylic acid functional group. So which one is going to be much stronger in this one? So here we have the same compound. What is only different is the halogen. So in this case we are going to compare the halogen. So this one has got a much stronger electronegativity than the bromine, and so it's going to stabilize the charge more by the, is going to increase the electron withdrawing effect by the inductive effect. So there is more electron withdrawing effect, and that gets to stabilize the charge in the first one. So it is going to be a much stronger acid. Let's consider this one. Which compound is going to be a much stronger acid? So again, we only have 2 carbons here. I'm going to show that. But we have got a fluorine at carbon number 1, and then we have got a double bond there, and then we have got the OH. But in the other one we have got 3 carbons. So 1, 2, 3. And then at the first carbon, we have got a fluorine, and then we have got also the carboxylic acid functional group. So which one do we expect to be a much stronger acid in this one? Well, we can see that this one, because the distance between the fluorine and the functional group is much higher, it means that it's going to be weak in terms of stabilizing the charge that is going to be formed. And so you expect the first one to be a much stronger acid because the fluorine is much closer to the functional group. So that is why it tends being a much stronger acid in comparison to the other one. Now, just another thing that I should be able to mention here is that the solvent in which the acid is affects the strength of the acid. So, for example, if I have got hydrochloric acid, now in gaseous form we call it hydrogen chloride, it's going to be a much weaker acid in comparison to hydrochloric acid, which is an aqueous. The reason for that is that when this one forms an ion, it's going to have, if it disassociates, it's going to have hydrogen ions and chlorine ions. So if this is in the air, these two are negatively charged, and so they are going to be more strongly pulling themselves like that. So it will be very difficult for you to lose this hydrogen, and the more difficult it is to lose the hydrogen, the weaker the acid. But when you talk about in aqueous solution, when you form this hydrogen ion and this chlorine ion, because you have water there, we have got what we call solvation. So by solvation, what gets to happen is that the water is going to be able to surround these ions. So the negative portion of water surrounds the hydrogen, and then the positive portion of water is going to surround the chlorine like that. So this is by solvation. And because of this, the ions are going to be stabilized. And remember, anything that stabilizes the ions makes that acid to be much stronger. So because these two ions are kept away from each other, that means that they can be easily separated. And because of that, this hydrogen will be lost. And that makes hydrochloric acid in aqueous to be a much stronger acid than hydrogen chloride, which is a gas. So the solvent tells us the more how strong the acid is going to be. So in the presence of water or in an aqueous environment, the acid tends to be much stronger. So another thing that I should just get to mention is that we have got protic and aprotic solvents. So I'm going to mention polar first, polar protic solvents and polar aprotic solvents. Now if we talk about polar, of course something that is polar means it has got a charge, and mostly when we see a bond between a carbon and an oxygen, this means that this compound is polar, right? Now sometimes it can be polar but it is not protic. What we mean by protic and aprotic is something has got a proton that can be released. So every time that we have got a bond between hydrogen with either fluorine or oxygen or even nitrogen, these are going to be protic solvents. These are going to be protic solvents. So those solvents, we refer to them as protic solvents. And then those solvents we do not have these kind of bonds, those are called aprotic. So examples of protic solvents that we can give is water, ammonia, because we also have such a bond. We can talk of alcohols like methanol, ethanol. These are protic solvents. But when we're talking about aprotic solvents, we can talk about acetone, right? This one, we have got a bond like this. We see this oxygen is not bonded to any hydrogen, so it is aprotic. We can talk about acetonitrile. We have got this compound. We have got this nitrogen which is bonded by a triple bond to this carbon. It is not bonded to hydrogen. So If we don't see these three bonded to hydrogen, that mostly is going to be aprotic. We can talk about, you see this compound. So this one, because there's a bond between carbon and oxygen, is going to be polar, but it is aprotic because we don't have a bond between oxygen and hydrogen. Alright, so that bond between hydrogen and oxygen can form hydrogen bonds with other substances. So when you are talking about SN2 reactions or SN1 reactions, each of these have got a kind of solvent that they get to favor where they are going to work well. Well, in that one, we are going to discuss that in the next tutorial, what kind of solvent, which kind of reaction gets to favor.